Welcome everybody. We have 1 hour, 50 minutes, and I tend to respect the time, okay? My name is Koen Bertels, Belgian by nationality, but I worked for about 20 years in Delft, which is neighboring country, right, the Netherlands. And that's where I started working. I'm a computer engineer, I'm not a physicist, to be very clear. Yeah, and as a computer engineer, I started working. I was invited by back then my engineering faculty to start working with the physicist to develop a quantum computer. Okay, so that is, and of course, I was leading the computer engineering group. We never ever looked at quantum computing. That's like, yeah, no, that will never work. Yeah, so but then you have to do it. Yeah, the physicists were expecting that we would collaborate. I was with a colleague, a Swiss colleague, Eduardo Charbon. He's back to Switzerland, to Lausanne. Yeah, but we started working on these quantum computing aspects from an engineering point of view. So the title for the course is like Introduction to. Yeah, I basically have no idea what to do in 4 hours. Yeah, because it's way too much to explain in 4 hours. But I will try to give you some intuition of what these quantum gates are, what these qubits are. Yeah, but I will most likely insist on what we're expecting from the young people, from you, yeah, and actually from other disciplines too, from other fields. So today talk is about NISQ, PISC, yeah, and the bottom line is the emergence of a new scientific approach. You can say, yeah, holy damn, again, some crazy guy coming to talk here, everything's going to change. Well, yeah, it is going to change. Not that I want it, but this is once you move into the quantum computing logic, it turns out it is orthogonal to what you actually know. Yeah, so let's walk through. Yeah, I started a company. It's my third company. Yeah, and you see here, no, they're not here. My colleagues are not here. Yeah, Imran is a professor, has Dutch nationality, but he's living in Pakistan for now. But he will come back to Europe once we have a bit more money in QBee, of course, right? Aritra is an Indian student. He graduated, well, a postdoc in Delft. He graduated with me last year in July. Yeah, and she, Tamara, she's PhD in chemistry. She's Serbian, but she lives already for about 10 years in Belgium. Yeah, she has 3 kids, just to make sure that the women who are also present here understand, yes, there is no balance, you can do your own life, yeah, but also step outside or inside a completely new field. Yeah, very important for women to understand that we do encourage women to make that step. Yeah, and so I will tell more about Tamara because that's one of the examples that we're working on, yeah, in the company. Yeah, and of course I do have PhD students. You have 4 here on row number 3. Raise your hands maybe a little bit. Yeah, Hongfeng, you too. Yeah, different kinds of fields. Yeah, so because that is what we're now going for, let's say the end user applications, that is what we understand by the PISC. Yeah, NISQ, you may have heard about that, that's noisy intermediate scale quantum, NISQ. That is what everybody in the world claims to be doing. Yeah, and we really need that. Yeah, so I worked with physicists myself for 7-8 years in Delft, actually much longer, but very intensively with 7-8 years, on all of the error correction, all of the physical problems that we still have not fully solved in the quantum world. Yeah, so that's why I said we have to step out, and so with the team that you just saw, we defined a new label, which is PISC, perfect qubits, intermediate scale quantum. And that's what we say, yeah, that we want to look more at end user applications again. Yeah, so because how many gates do we have? These are operations that you perform on these qubits, 20. Yeah, if you want to build a universal computer, you can never do that with 20 gates. On a laptop like this, we have around 10,000 logical gates. More powerful machines up to 100,000 or even higher numbers, yeah, of quantum gates, logical gates that we do to build a universal computer. Yeah? So this is clearly not enough, and that's why we need to look much more at end user applications and start defining what we find there. Yeah? So whether you like it or not, computers will not disappear. Yeah? It's not that I'm going to say, forget it, in 20, 30 years you will not have a single computer. No, of course it will be there because it's so penetrating the world, our daily lives, from the dishwashing machine, yeah, up to our car, to factory engines, machines, etc., etc. So that will absolutely stay. You heard also yesterday the person from HiPEAC, yeah, it was clearly a digital computing kind of a challenge or story that he was bringing. Yeah, and I already had very interesting discussions with some of the students that I met. But you do see those things will of course continue to exist. Yeah? Now, many problems that we are confronted with in daily life, whether we like it or not, yeah, are of a scale and an intensity and a complexity that we don't even know how to handle. We cannot build sophisticated and large enough models to run it, let's say, on a supercomputer, and then we'll come out with solutions. And you see that, for instance, in optimizations. Yeah? And just imagine that you have a dinner at home for 10 guests. Yeah? And the number of combinations for these 10 people to put them in various ways together with each other on a table, well, it goes into 3,000, more than 3.5 million combinations. So how can you, usually it's a bit of a random choice, yeah? Nobody is going to compute those kind of things. Yeah? But you also have chemistry. Yeah? I mentioned Tamara in the beginning, yeah? PhD in chemistry. Yeah? So she worked in industry. She worked also for, let's say, a nuclear research plant in Belgium, yeah, and she kind of understood very well what all of the aspects in chemistry are about. And then it was like, now it's already 6-7 months ago, a couple of months I gave the same example, yeah, but it's already 6-7 months ago, she came to me, oh, yeah, and she said like, Koen, I thought I understood a lot in chemistry, but now we're doing this quantum computing logic way. It's completely different. I understand nothing anymore. She is very smart. Let's be very serious. That's not what I'm saying. But it is so radically different. The way that we have to reason and formulate the solutions and the methods that we need for any quantum operation are completely different. Yeah, and that is basically the thing that we're going to be working on. Yeah. So, what is this quantum computing all about? Well. I've not met a single physicist, and I've been working a lot with very smart people. Leo DiCarlo is still a very good friend of mine. He's still a professor in Delft, yeah, and he works on one specific kind of qubit technology. Because maybe 5-6 years ago, there were like about 10 different kinds of qubit technologies. All the physicists say, we make the best qubits. Yeah? Now, it has already been shrinking, but been reduced to, let's say, 5, 6, 7. Yeah, but still, the photonics is still there, the ion traps. The last physics Nobel Prize was on cold atoms. I never even heard about that word. Yeah, that's my lack of knowledge, of course. Yeah, but my superconducting, ion traps, photonics, so many different kinds, and they all claim to be the good qubits. And from a computer engineering point of view, when you build a computer, you want to look at, let's say, what are the problems that arise when you do such a computation. Yeah, and I will give numbers about that. But if you compare it to, let's say, CMOS transistors for classical machines, like the one that I'm using here, that you have in your cell phone, yeah, we have up to 10 to the minus 15, minus 16 kind of errors. Now, how big is that as a number? 10 to the minus 9 is 1 billion. If you multiply the 1 billion by 1 million or by 10 million, then you have 10 to the minus 15, minus 16. Yes, we can handle those kind of things. Even though yesterday evening you saw how many steps in the full stack interface, yeah, that you have, let's say, from software to hardware. It is incredibly long. And I've been talking to 2 student groups so far, and they all want to add another layer to this kind of thing. I said, yeah, okay, good, finish your PhD, but you have to also think about these quantum challenges too. Yeah. So that is what do we see here? Yeah, we have very important. We're in the analog world suddenly. Yeah. I was working for 20 years in Delft. We only had basically digital courses, yeah? Yeah, from mathematics to software to hardware design, electrical engineering. I was only like looking at the digital engineering kind of things, yeah? But suddenly, yeah, so analog, yeah, sure, we have some analog courses too, yeah? But suddenly if you go into the quantum world, all of these quantum phenomena are analog phenomena. Now again, say, yeah, an analog, but again, the analog, if you go for, let's say, a superconducting electron or a semiconducting, yeah, and we're not having the large number of electrons, yeah, which we have in classical machines, even in the cell phones that we're using, we have billions of these transistors, yeah. So we need to go, let's say, to much lower kind of electrons, or photons or neutrons or whatever it is, yeah? But that is what we're going to be manipulating. So not these huge numbers that run through a classical circuit. No, a couple of those electrons, and maybe it's 50, maybe it's 5,000. Yeah, you hear different kinds of numbers. People don't really know yet how many we need. Yeah, but it is going to be relatively much lower. Yeah, so that is, and then they can either reinforce each other. Yeah, so constructive. Yeah, and then they strengthen each other, or they cancel each other out. And then you basically have no effect. So these are the two main challenges of how to perform an operation on these qubits. Yeah, qubits are quantum bits. Yeah, and so so this is what you see. This is the analog kind of thing. Yeah, these are all wave functions. So you see a graph here of a wave function. So either they reinforce each other, or they simply cancel each other out. Yeah, that is how you make a particular value for a particular base state. We need many more people than we already have. Yeah? There were a lot of mathematicians that came into, let's say, the quantum computing world, and that's about, let's say, in the 1980s. Yeah? So it started actually with 1980s, I think 86, when Richard Feynman, the famous physicist from the United States, yeah, who was really super focused on all these quantum mechanical phenomena, he said, like, we don't really understand what it is that we're talking about. Yeah? And he said, like, that was 92 or 1986, I don't know these numbers, sometimes they vary a little bit in the reference you see. Yeah, why don't we simply build a computer based on these principles? And so that immediately launched a lot of physicists and mathematicians to start looking at what are these phenomena that we're looking at. Yeah? And that's also when the notion of perfect qubit was defined. Not by me, not by the QBee team or anybody else. That was defined from day one in the quantum computing world. Yeah, let's simply assume it does exactly what we want it to do. That's where the name perfect comes from. Yeah? And then what kind of operations are we performing on these things? Yeah? So we've discovered in the meantime that there are so many things, yeah, popping up in terms of problems. Yeah, and errors that we have to correct. Yeah, I will mention some of these things. But so you see here, yeah, there is the BQP, that's quantum polynomial, yeah, polynomial, NP complete. So it fits in a particular way, but it's not clear yet because these are pretty vague boundaries. Sometimes they overlap. Yeah, so again, we need also people that are interested in those kind of things to look at it. Yeah, well. You have some kind of mathematicians, yeah, and they're very close to physicists, yeah, and one of them is Shor, he's an MIT professor, and he came with an algorithm to say, look, we have a big number, and we need to generate or determine what the prime numbers are. When multiply these prime numbers, give me the big number. Now the multiplication is not difficult to do, yeah. You can even do that on your phone, but doing the reverse, finding the prime numbers that multiplied together give you this particular number, that is an incredibly hard problem. Yeah, and so NP complete, or even worse than that, I don't know. I'm not a specialist in these kind of things. Yeah, but this is what Shor proved, that if you have a quantum algorithm, and he defined the quantum algorithm, yeah, you can actually very easily decompose the large number into the prime factors. Yeah, and so one of the PhD well, actually he was a professor in Delft back then, yeah, and he did it for his PhD in Stanford, the number 17. Yeah, so that's kind of, yeah, okay, that's we can understand that, yeah, but he developed a quantum circuit and some qubits, yeah, physical qubits, to actually make that decomposition. So that is important that we understand that there's a link with so many sciences together. Couple of important concepts that you need to understand whenever you go in quantum, yeah, and you have the slides, yeah, and I may have changed a couple of the ranking of the slides, yeah, but all the information is in the staple that you have, yeah. There are also a lot of exercises, yeah, and I asked all of my students, you guys verified that all my errors, all my examples are correctly solved, yeah, so they did everything. If it's wrong, I'm still to blame. Yeah, I don't want to blame anybody else because I'm responsible for it. Yeah, but I think we kind of solved it, even though 3 days before, yeah, I was still looking at the slides and like, oh, God damn it. Yeah, there's something wrong. This is not possible. Yeah, yeah. But okay, we're using these Dropbox. You may use these things too, and sometimes it goes back to a server and then it puts it again on your machine. And I don't know, maybe something must have, yeah, gone wrong there. But okay, yeah. So I will tell you maybe when I go through that particular slide what it should be, or ask you. So what are these concepts here? Superposition and entanglement. That is when you want to combine multiple qubits. Again, I have to make it a bit theoretical now. So every qubit, quantum bit, has 2 base states, 2. And let's make it simple. The computational base state is 0 and 1. In a very specific way written, is a Dirac notation, but that will come later on, So it's the 0 or the 1, and every base state has an amplitude, has a parameter, has a number, a complex number, so as a real and the imaginary part, and that determines with the probability, if you look at it in a particular way, what is the probability that is 0 is the correct answer to your quantum circuit, or the 1 is the correct answer to your circuit. If I'm combining 3 qubits, each of them has base state 2, it's 2 to the power 3, is 8, then it becomes 16, 32, 64, then it immediately goes very rapidly in the large number of base states that you have. What is important to understand is that when you have, let's say, these 3 qubits, 2 to the power 3, that gives us basically 8 different kinds of data layers. And this is something that you read that is, for me, was very difficult to understand, so I try to be clear on it now. Whenever you have these 8 layers, it's a multi-dimensional universe that you're creating, mathematically, but also in the quantum mechanical world. This is something that you don't see. It's not like a projector or a 3-dimensional object. No, it's a multi-dimensional kind of matrix that you're generating, and it all goes into this quantum world. Again, nobody can explain that, we only know how to induce that, also physically, mathematically, and also as engineers, we try to use those kinds of features. But if you have, let's say, 2 to the power 3, so these 8 layers, that is in superposition, these 8 layers. So I have 8 different paths, and what are these paths different in? Because the base states and the amplitudes will be different on each layer. And when I have, let's say, 10 gates, 10 steps in the quantum circuit that I have to make, I will do that on those 8 layers at the same time. And that is why I write down there, it's implicit parallelization. Implicit. When we talk about supercomputers, yesterday evening, we had very good examples yesterday evening, but from the classical world, you can have, let's say, 10,000 logical gates on this, 100,000 on another machine, maybe several millions on supercomputers, but how do we use supercomputers? We cut them into pieces. Here, that's one for you. Another piece, that's one for you. That's how we split it up into doable kind of machines. We never program at the level of a supercomputer, never. Nobody is capable of doing that. If somebody, if I'm saying something wrong, you have to, yes, I can do that, then I will invite you my team, and you have to show me that. I never met anybody so far, and I've been active in the academic or the university world already for quite some time, so if you do this implicit, because if you do it in a classical way, you have to do an explicit parallelization, Path 1, path 2, path whatever it is, 10,000, whatever it is, and you have to make sure that you take all of the values of your variables into account. Not in the quantum mechanical logic, in the quantum computing logic. That is done in a very intuitive way. So once you have a quantum circuit that you generate, then it will be executed in all of those dimension states at the same time. If then we're used to working with computers, right? And we want to have the result. What is the result of my quantum circuit? So I have, let's say, these 8 different layers. What is happening when you say measure the result? You lose all of those states except one. And that's going to be thrown at you as an end user. What does that imply? You have to repeat the same algorithm, the same quantum circuit, multiple times. And each time say, what is the result? You get one result back, and you have to do it, and then you get some kind of histogram. And the final base state, which is measured the most frequently, is the one which has the correct, most likely has the correct result of your quantum circuit. So these are things that are completely orthogonal to the classical way that we're developing, that we're programming, that we're building systems, completely different. So if you say, it cannot be so difficult, it is incredibly difficult because it really changes your way of thinking about how to represent data as a qubit, Yeah, and what kind of quantum gates do we operate on these qubits? Yeah, so these are some of the examples that you will see, yeah, this week that I show them. Yeah, there's entanglement. That's another way of superposing kind of qubits. Yeah, but what is the difference between superposition and between entanglement? Is that when superposed qubits, you can actually decompose them again. Yeah, these are. We know this mathematics basically, yeah. So it's again, we separate these matrices and we go, this is qubit 1 and this is qubit 2, yeah. But when you entangle them, these matrices are completely intertwined, and you cannot separate them anymore. Yeah. So this is again, yeah. So like again, say, yeah, well, holy damn, what am I doing here? I want to go back to a different course. Everybody's free to go, right? That is absolutely true. Yeah, but if you really want to understand what this quantum computing logic is all about, well, then you better stay, because you're all pretty young, according to me. Yeah, and so this is something, the quantum computing will be part of your lives. Maybe of mine, I don't know that, yeah, but certainly of your lives. So you have to, yeah, and as an engineer, you can look at the physics part, but you can also start looking at the application side. We're basically in between. I will show that later also when I give the examples. Yeah. So well, well, the full stack. Yeah, that's what. Yes. Oh wait, we have a. Wait. There's a microphone. Who has a microphone here? Yeah, because otherwise we don't hear you, huh? Switch it on also, Kuros. Then I will try to repeat your question to see if I understood it.
It doesn't have so much to do with quantum computing itself. It has more to do with physics. But you say that entanglement goes way more fast than the speed of light. How would a human being, or how would we be able to test something which is an order of magnitude 3 times faster than the speed of light, and how you can measure the speed?
Yeah, well, okay. I will give that example actually later on, yeah, because that was one of the first experiments that in Delft they did, yeah, and they had to go, let's say, more than 1.5 kilometers away from each other, yeah, and full entangled, and then they could actually see that the full entangled qubits, when you change one, it's measured at exactly the same moment, 1.5 or 2 kilometers away from each other, such that there can be no transfer of information at the speed of light. Speed of light stays a mathematical law and a physical law. You can never go faster than light to talk to each other, yeah? But that doesn't mean there may be other forces, and in the quantum we know there is a force that connects those two qubits, full entangled qubits, yeah? So again, that would lead us very far to explain, because yeah, I only know that we can do that, yeah, but I cannot, nobody can really explain what is going on, because this is a force that we don't even know where that comes from. Yeah, so that is yeah. Okay, so there are always waves. I already said that they can reinforce each other or cancel each other. This is how these quantum phenomena are. Yeah, I will go a bit fast over these things now. Yeah, I want to refer to, let's say, yeah, I'm Belgian. I worked for a long time in the Netherlands. Yeah, but still, okay, certain things also do happen in Belgium. Yeah, and there was a conference by Ernest Solvay. Yeah, he was a chemist, and he created a company in Brussels. It still exists. Yeah, and he organized every year a conference for the physics people. And so this was in 1927. And you see here, is there a Polish person in the room today? No? Because this is Marie Curie. You may not recognize her, but this Marie Curie, yeah, sounds French, but she's actually Polish. She was married to a French chemist too, who got the Nobel Prize basically on her work. Yeah, see, well, these are all personal things. That's what it is. Yeah, but you also see here, yeah. So that's Marie Curie. Here, Albert Einstein, that we know. Yeah, and this is Niels Bohr. If there are Danish people here, they should be proud of the fact that quantum mechanics was actually initiated as the first time by Niels Bohr. There's still a very good quantum research center, the Niels Bohr Quantum Research Center in Copenhagen. Yeah? But this was immediately the start of, let's say, the relativity theory and the quantum mechanical theory. So like, yeah, Einstein said, no, this is ridiculous. It cannot be. Yeah, you can never have these forces. Yeah, blah blah blah. So this immediately mediated, yeah, a lot of discussion between these two. And actually, then Einstein wrote a paper with Podolsky and Rosen, yeah, the EPR. Yeah, and he one of the reasons why he got the Nobel Prize was because of that, among many things, of that particular kind of quantum mechanical paper that he wrote, which kind of was the proof that he was wrong. Yeah, but it's still being used very actively in the quantum world. Anyway, so these are things. My personal background, what do I know? I always say to my students, I know nothing. Yeah, that's the worst thing you can say as a promoter, of course. Yeah, but until they realize that you do know certain things. Yeah, but so I started to work, let's say, in 2012, so that's 11 years ago. Yeah, in Delft. Yeah, after working on classical FPGAs and all kinds of computer engineering things. Yeah, so I want to highlight maybe a couple of things. One. You know Intel. I do hope that you guys know Intel, right? So Intel, yeah, they also realized so many years ago that they have to look at this quantum technology as a successor for the old kind of CMOS transistor. What is the size of a transistor these days? 2 nanometer. Yeah. Once you go, yeah, that's even IBM is announcing a 2 nanometer kind of computer chip. Once you go below the 1 nanometer, you immediately enter into the quantum mechanical universe. So either you can ignore it or you can embrace it. And that is what many companies do. Intel, Google, yeah, IBM, Alibaba in China also does that. Yeah. So anyway, at some point I said, okay, we need also much more application oriented, and that's why I created the QBee here. Oh. Yeah, yeah. So that's why we created QBee, and I showed already the 4 people, yeah, leading that together with me. Yeah, and so I worked with a lot of universities, but also with companies and research, and business consortia, business clubs. Yeah, the QUIC, yeah, came out of the quantum flagship. You may have heard that there's in Europe, there's a quantum flagship, basically too much dominated by the physicists. I understand that. But they also have now the QUIC, which is the Quantum Industrial Consortium, QUIC. Yeah? And so I've been, let's say, a month or a month and a half ago, they had a 2-day meeting in Madrid. Yeah? And QBee as a company is part of that. Yeah? And in the meantime, I'm now part of this quantum computer architecture group, blah, blah, and all these kind of things. Yeah? So again, classical machines, it will stay there. This is not going to disappear from our lives. We cannot even imagine a daily life without the use of classical computers. Yeah? They're literally everywhere. Yeah? But so for instance here, yeah, we're talking about zettabytes. That's 10 to the power 21 number of bits that you're using. Yeah? These are incredibly big data that we have. Yeah? But we don't really know how to analyze these data. Yeah? Why not? Well, you have the planet, our planet, is founded on the internet, yeah, yeah. So this is the reference, yeah. It's the planet. But if you look at the amounts of data that we are collecting on a daily basis, everybody takes pictures. For sure, you must have taken maybe already 10, 20, maybe more pictures of this summer school, HiPEAC in Fuji, yeah. And maybe last week with your friends, or I don't know. It's incredible, yeah. Where do we store that? Yeah, it's on my phone. No, it's not on your phone. It's most likely on a server on the internet where all of the things are stored. Yeah? And if you look at all of the data, and if you look at, let's say, yeah, these electrical cars, but if you look at factories that are, yeah, I already mentioned the chemistry kind of things, all of the chemical products are based on computer products, yeah, on computer algorithms, yeah, so, and they have to reduce the size of the number of electrons that they use to circle around the nuclei, etc., etc. Yeah, so this creates huge amounts of data that we don't really know how to analyze. Yeah, so so that is the reason, one of the reasons why many companies, yeah, I already mentioned them, yeah, make this choice towards quantum computing, yeah, so that they really understand, like, wow, we really have to completely re-innovate the way that we're thinking about computing, about data, how to use data, how much data, how to represent it, etc., etc. Yeah. So here you see this is for superconducting or semiconducting, but this is for superconducting qubits. So usually the quantum chip is somewhere low here, yeah, and that's in millikelvin. That's 20 millikelvin. 0 Kelvin is minus 273 point a lot of things Celsius, yeah. So that's the absolute 0 point, yeah. So we're very close to the absolute 0 point. So these things, they're in a barrel of helium, liquid helium, yeah, so that you can cool all of the things inside. Yeah, and then the higher you go, the more digital it becomes. And that's my colleague, yeah, good friend, Eduardo Charbon, now in Switzerland, he worked on cryo-CMOS, so to make classical CMOS digital technology operational at very cold temperatures. Yeah? And so once you go out, you're in room temperature, Yeah, but okay, that is what you have to do. So, yeah, this is of course you see companies, even Amazon. Yeah, yeah. Jeff Bezos is one of the founders of Amazon. He also finances a lot of research in quantum computing. So it simply shows there's a lot of interest. Again, I showed the Moore's law, that the doubling of the classical transistors every 18, 19 months. It doubles in numbers, yeah? And this is, let's say, the black one. In 2005 only, Intel started introducing coprocessors into a computer, yeah? And then you do see that there's a rise in compute power, yeah? But it's stopping off again. So it's not growing in the same way anymore as, let's say, the number of transistors that we're using. It is not, yeah? So these are the challenges, yeah? I will skip this one, yeah? So again, what is the mathematics now? Yeah, and yes, I will go through the mathematics most likely tomorrow. Yeah, it's a tensor mathematics. There are different kinds, but tensor was invented as a technology, as a mathematical theory, let's say 70, 80 years before the quantum mechanics was defined by Niels Bohr. Yeah, but it turns out to be a very useful tool, yeah, to express all of these quantum states. Again, here I have one qubit with two base states. Yeah, so the 0 and the 1. So this is the Dirac notation. Yeah, so the vertical sign, yeah, and then the number 0 or 1, and then the big one to the right. That's the Ket notation. And if it's this one is on the other side, it's the Bra notation. These are just ways to represent qubit states. Yeah, qubits. Yeah. And so here is the qubit psi, has two base states, 0 and 1. And the 0 and 1 have each these amplitudes, yeah, the alpha, beta in this particular case, alpha and beta. And these are always the parameters on which we perform any kind of quantum gate. Yeah, and so that will then keep on growing. It can grow bigger or smaller. Yes, it becomes -2. Yeah, and if you then reorganize it, but I will say it on the next slide, yeah, reformulate these amplitudes in a particular way, you get the probability with which the 0 is now the most likely candidate of a final solution, or the 1. Yeah. I can have two qubits, so then I have 2 to the power 2, 4, 1, 2, 3, 4. Yeah, and again with 4 parameters. And I can go to any number. You can even go, let's say, up to 300 qubits that you put in this superposition mode. That's 2 to the power 300. And I must have mentioned maybe with somebody that already had lunch or dinner yesterday with me. Yeah, this is a number that I cannot even express in English. Yeah, because this, I read that somewhere, is so big, is bigger than the estimated number of atoms in our universe. Yeah. Where we have, I don't know how many, so we used to have 10 planets, but we have many more planets these days. Yeah, so if you put all of these atoms on all these planets together, this 2 to the power 300 is bigger than the number of atoms. So this simply shows that this is the compute power that potentially and theoretically we have. We are not at all there. Let's be very clear about that. Yeah. So this I think is very important to understand. Yeah, I already said that. Yeah. What is important? Yeah. Again, the properties of what we compute are very important, because it is, two words here, non-deterministic and reversible. Yeah. So if you can go from left to right, yeah, you can also go from right to left. Yeah. So the initial state on the beginning of a quantum circuit with all of the base states that you have, yeah, you perform all of the gates, you will have all of these different layers in superposition. Implicitly, it's a multi-dimensional kind of universe that you're generating. Yeah, it is a mathematical concept, but it is really happening. Yeah, then at the final quantum circuit gate, you say, okay, now I get the result. As I explained, you do the measurement, you need to repeat it multiple times, and then you get the final result of the most likely, yeah, measured kind of final base state that you have. Yeah? So this is what we call, yeah, non-deterministic, because it is so much driven by the probability, yeah, of these amplitudes, because it is computed in, let's say, the absolute value of the amplitude. Yeah, just a second. Yeah, Kurosh, you can already go to that person. Yeah, if you go to this the absolute value squared of all of the amplitudes, that always equals a 0 or a 1. Yeah, or 100%. Yeah. So you have a question?
How you determine how many times you need to repeat the measurement?
Nobody knows. Yeah, if I don't know, I will not say yes so many times. Yeah, this is something because, of course, you can. Yeah, this is because we still need to figure out. Yeah, what is driving, let's say, this formula? Because maybe there's a formula somewhere. Is it the number of qubits? Yeah, the number of base states? Is it the number of quantum gates? Yeah, we really don't know. Yeah, so now what we do, even in the PISC, yeah, actually in real life, yeah, the John Preskill is one of the physicists. He initiated this NISQ idea, and he said, look, don't go for a crazy number of qubits. Let's say 100 qubits, and random quantum circuits, yeah, with quantum gates around 1,000. Yeah, but we have to make them really, really good. Yeah, really improve the quality of these qubit states. Yeah, so again, we don't know how many that is. For a random circuit, that's kind of okay, 1,000, then you're ready. If you only have 20 gates for now, only 20, yeah, that's kind of okay-ish to do. Well, I did that with Leo Di Carlo in Delft too. Yeah, so that is kind of doable. Yeah, you can generate these circuits, that is fine. Yeah, but then how to improve, let's say, to make these things stable again, yeah, that would be, I'm not going to, maybe I will mention surface code again at some point, yeah, but we don't really know, yeah, how to do that. But anyway, so this is the non-deterministic, the probability is driving, yeah, and each time you have to make, yeah, sometimes you take a very low probability kind of path, but you'll report that anyway, and maybe there will be one probability state, final state, which has the highest probability, and that is measured most of the time. Yeah, and reversible, if you go from left to right, you can also go from right to left. You need, of course, what your final states are on the right, and simply do the reverse kind of quantum gates to the left, and then you'll end up again. Yeah, so one initial state here will always get you the same final state, but if I have maybe thousands of base states, yeah, you need to do that for all of these things at the same time. So this is what we mean by this reversible kind of computing, which is not true in classical logic. Yeah, yeah, you cannot do that because you lose many bit information, but with every logical gate that you perform. Yeah, so again, these are important properties. Do we think there's a market? Well, I start a company, it's my third company, so yeah, I do hope there's a market, right? Yeah, and this is like, this company, yeah, estimate this market to be severely growing, yeah? And we'll have to see how far we jump, yeah? But I will say something a bit more about that later on. So this is just like, these are McKinsey, you may know that is a consulting company. Yeah, and I will talk about Gartner, which is another consulting company too. Yeah, yeah. But McKinsey looks also at the bit of the market, and I indicated here with these arrows the things that we as QBee want to be doing. So yes, we look at hardware, but we're not developing hardware ourselves anymore. So we look more at applications, microarchitecture. Yes, and we have our own simulator with perfect qubits. Yeah. So this is simply saying something. This shows you. That's actually one of my Chinese students. He took pictures of all of the evolution of all of the full stack layers that we have. Yeah, Shangfu. Yeah, he graduated with me in Delft. 1 week later, he was back in China, professor. Yeah, he has 2 research groups. He got a lot of money from the Chinese government. Yeah, this is unfortunately not the way it goes in Europe. Yeah, or I don't even think in the United States. Yeah, but in China, yes, that is the way that he goes. Yeah, so but in any case, he showed all of these pictures. And he sent that to me. He said, okay, that's good to see that we really started on the whiteboard. Yeah, what is it that we should be working on? And of course, we start with the hardware part, the hub. Yeah, and this is our latest. Yeah, this is what we now want to be doing within QBee. Maybe I will talk about that later. Yeah. So here again, it's the same kind of thing. These are the topics that we in QBee are working on at the top layer. Yeah, and yes, I do have a customer, yeah, which is a space company, yeah, Telespazio, which is an Italian-French company, yeah, founded by 2 large companies in Italy and in France, yeah, and so we work on aspects for satellite images and things like that. We'll also look at defense, quantum chemistry, that's what Tamara is doing, yeah, and genome sequencing. Yeah, I will not give a demo today because I will give a separate version on the genome sequencing kind of algorithm. That's what Aritra did for his PhD in Delft. And I will give a live demonstration of that algorithm that I connect to the server in Leuven, yeah, and and get the results over the internet, yeah, back from that server machine where the software is running, the simulator is running. Yeah? And I did a similar kind of talk in Australia, it was earlier this year. My son lives and works there, yeah, in Sydney, that's very nice for him. Yeah? So I went to visit him, but I also visited UNSW, which is a university in New South Wales in Sydney. Yeah? And I met I met him actually, Andrea Morello, in Delft. Yeah? He's a physicist and he works on semi-conducting qubits, but 2-3 different kinds. Yeah? But he wants to make them really, really good in terms of coherent. Yeah? That you don't lose that information, and that goes up to 5 minutes. And he tests all of the quantum universal gates also on these qubits. So he looks at a very low number of qubits, not like IBM and Google and there are large numbers. Yeah? They make a lot of claims, but at some point we need to integrate, I think, those two kinds of lines of research. I mentioned to one of my German colleagues here, yeah, Professor Lehmann from Stuttgart. Yeah, so he is very enthusiastic about this PISC approach. Yeah, so PISC stands for this perfect qubits intermediate scale. Yeah, to really say, look, don't look at all of the errors that you get. Yeah, simply assume these qubits do whatever you want them to do. Yeah, and this is already a very challenging kind of thing. Yeah, as I explained from Tamara. Eh? So at some point, this NISC and this PISC, we can bring them together again. Yeah, but why aren't they not together right now? I already mentioned those numbers. The green one here, yeah, there should be minus, but the number is important, right? When you look at CMOS transistors, base is always 10. Yeah, 10 to the 15 or 10 to the 16, so this is a billion to the power 9. You multiply by a million or by 10 million. That is how many errors or operations you can do on a classical machine, and yes, we can fix those things. Don't ask me now, I never dove into those kind of things. Eh? But this is what we do. In the quantum world, every 100, yeah, or 1,000 operations that we do, you lose everything. I said, like, so that's why I said, like, Leo, yeah, good friend, Leo Di Carlo, Argentinian. I said, look, Leo, when are you guys going to really move up? Yeah, because I would like to see what you do in 6, 7, yeah, 8. Yeah, because they say, yeah, the computer engineers like me, that you guys will solve it. I said, no, Leo, no. This is not possible. I don't even know how to solve it. Yeah, so this is really a challenge for the physicist. And he's basically an engineer, to be honest. Yeah, he's an engineer, but turns into a physicist. Yeah, for these quantum things. Yeah, but this is why now we need to separate these things. So yes, NISC, absolutely, we need that. We absolutely need that. Yeah, but we also need much more this PISC kind of idea. Why? How many gates do we have? 20 gates. 20. The universal quantum gate set, 20 gates. How can you build a large-scale universal computer with 20 gates? This already has like 10,000 logical gates. Yeah, up to several hundred thousand of logical gates in classical machines. With 20, you cannot do anything. Yeah, so this is why we already show, yeah, that it's important to move around. Yeah, blah blah blah. Many people are interested in those kind of things. Yeah, and it is indeed a new way of thinking. This shows you what are the qubit technologies currently still in the market. And you do see superconducting. IBM is doing that. Intel is in the semiconducting. Yeah, that's the quantum dots. Semiconducting, but you have Google, Alibaba, Riget, there's several smaller companies in the United States too. They work on superconducting qubits. Will that win? I don't know. I can only hope. I mean, yeah, I do hope it will win, but I don't control these kinds of things. Yeah, you have photonics, you have ion traps, and different kind of things. Yeah, so here I mentioned neutral or cold atoms. It's very diverse. Yeah, and they all claim to make the best qubits. And I say, look, as a computer engineer, I say they're all bad. Yeah, and that is not to discourage you guys, yeah, because I do believe this has a huge potential of compute power and data processing that I have never ever seen. Yes, and we looked at 3D CMOS transistors. Yes, sure, we looked at these things too. People are still doing that, membristors and all these kind of things. Yeah, we need the digital technology will also still need to evolve, but for the real big kind of data problems, we need maybe a quantum machine. Yeah, this is just an overview. It shows it in the slides. Yeah, this is another company that I wanted to mention, Gartner. Yeah, it's a consulting company from the United States, and you see here, they define themselves the hype cycle. They looked at so many technologies, yeah? And they say everybody's incredibly enthusiastic in the beginning. Yeah, this is amazing. It's going to change the world. And then you reach the top, you say like, damn it. None of these things actually deliver. So that's the hype, yeah? When you say a bit, all the companies and universities say like, forget it now, we'll step out of it, yeah? Then you get a decline, yeah? And it's only at a very much later phase that we will see things popping up again. And this, I think, is also happening in the quantum world. These are slides, yeah, from 2018. I have never found a similar kind of hype cycle figure from 2019 on. Never ever. If somebody finds it, please take a copy and send it to me. Yeah? Because that basically means like, whoa, we have to be a bit careful here because yeah, we're changing the world. Yeah? There's new technology, but if it fails, we're globally responsible. Yeah? So we have to make sure that we keep on, yeah, we have to keep on making people into our companies enthusiasts to keep on investing into that technology. Yeah. So anyway, that is a bit and I added here this red and this dotted line myself. That's what universities, very difficult to motivate to go to quantum, by the way, but companies do. Yeah. So that is already very nice to see. Yeah. Andreas Walraff is a professor at ETH in Zurich. Yeah. And he also talked about this hype cycle. And that was like 2 or 3 months ago that I found these slides, yeah, on the internet. And his Twitter, I don't know what kind exactly he uses, but this is D-Wave, very famous Canadian kind of company. Canada is very strong in quantum. Yeah, D-Wave, yeah, is a company, yeah, which is bought by all the 3-letter words in the United States: FBI, CIA, NSA. Yeah, they all have D-Wave machines. Yeah. Yeah, they claim to have several thousands of qubits. Nobody knows what kind of qubits. Nobody reveals that. Yeah, yeah. But they also we're looking now at this individual gate operations too. So again, maybe that will stay alive, and I do hope. But you do see here that the value goes to basically maybe it's like 10%, 15% of its value. Yeah, and you see that also with other kinds of companies. Yeah, IonQ. Yeah, that's I think that's whether that's well, these are the New York market. Eh? So yeah, I add a little comment, blah blah blah. That is my PISC idea. Yeah. So again, this is just repetition. Just that we should not forget where we are and what we're capable of doing. We are not there yet, and we need young people like you guys finish the goddamn PhD, but then say, now I want to do something for your postdoc or for whatever position you do in a company. Yeah, you want to look at, say, at this quantum computing logic kind of thing. Yeah, this is very important. Yeah? The NISC and the PISC, that stays, of course, very important. Yeah? But why is it important? And I will only highlight here number 4. Yeah, how much time? No, I still have, let's say, enough time, right? Yeah, so I will, so it's quantum computing logic. Yeah. When I started talking about these things, yeah, the physicist said, hey, quantum logic, Bertels, we do that, right? We're physicists, we work on quantum logic. I said, oh, okay, you have to respect everybody's ego. So now we call it then quantum computing logic. Yeah? So we say, look, we're not looking at the physics anymore, we look at the end user application. So we simply assume perfect qubits, yeah, sure. Yeah, we look at the top level. Yeah? So that is what we understand by QC logic. And I think this is an easier starting point. It still stays incredibly difficult, yeah, but you will find that in the next lessons, yeah, yeah. What we're doing, and that's what Aritra did for his PhD, yeah, for let's say quantum genome sequencing and for other kinds of algorithms, quantum circuits. He completely discovered completely new quantum gates, and of course you can either say the new quantum gate, if it's really intensively used, it should become hardware. As a hardware implementation, yeah. But you can also have the compiler do the translation of a very complicated quantum gate into the universal gate set, yeah. And that is what we had to do, of course, because yeah, we don't build the quantum physical hardware. We can simply, as a computer engineer, define what quantum gates should be part of any kind of quantum hardware, yeah. And we also have, let's say, a PISC simulator, so the perfect qubit simulator. Am I the only one to do that? No. Luckily, you have, let's say, companies like IBM. The Qiskit platform from IBM is very powerful, for free. You can download it for free. Yeah, so if ever you're interested, yeah, well, do look at Qiskit, which is a free downloadable kind of quantum software, yeah, where you can do also simulations for perfect qubits, but also for the superconducting kind of qubits, the ones that IBM is making. And they update the error rates that the simulator is using, they update that really, yeah. And if I'm going to give later this week to talk about the genome sequencing algorithm, I will do this live demonstration and you will see indeed, yeah, the results from the 3 kinds of simulators that you can get from Qiskit. Well, the third one is the IBM, is the QBee simulator, yeah, and we had a student for his master thesis in Delft, yeah, he made the PISC simulator for us, yeah, so that is very good, yeah, so it's not super complicated. If you can do it for a master thesis, it is still complicated enough, but okay, that's what it is. So again, repetition again, to make sure that everybody is aware of these multiple layers of the full stack, yeah, that it is where you're at the physical qubit layer, yeah, so a lot of the physicists, they're working in this black box here, yeah, Leo Di Carlo, Liebe van der Sijpe, yeah, in Delft, they still work on these things, what IBM is doing, what Intel is doing, Google, Alibaba, they all work on this quantum physics kind of aspects. So if you look at the big picture, it's a relatively small community, yeah, and we need to look much more, let's say, at application side, yeah. I have colleagues now in Porto and in Norway that are working on quantum, yeah, verification and validation. Because it's not the same, let's say, yeah, well, sure, but we do that already for years in classical computing. Well, yeah, true, but it's completely different if you do it in a quantum logical way. The logic is really completely different, so you have to really understand what it is that you're doing, and defining, yeah, and the testing and the validation of the quantum software is completely different. Yeah, so that is a layer that we added also because of the collaboration that we start having with them. Yeah, I worked a lot on those lower layers here. Yeah, in Delft, we developed the team that I had. Yeah, we developed our own programming language. Yeah. We have, of course, the instruction set that we supported, yeah, in the microarchitecture. We went to physical qubits, but now we also want to go, let's say, to the perfect qubit simulator. Again, that brings the PISC and the NISC software and hardware together at some point. Are we there? No, we're not there. Because we need also, let's say, an international. And you can say, okay, we're in Europe, so yeah, reason in terms of Europe. Yeah, but it should be done at worldwide level. But yeah, okay, you don't control anything, of course, at the world level, yeah, not even in Europe, yeah, but okay, my suggestion is, yeah, that we look at different kinds of field, chemistry, biomedical, space engineering. You already see, I'm only talking about things in which we are active, yeah, and we're talking to universities, to companies, and we should have, let's say, a PISC kind of approach, so that we abstract away from any kind of quantum physical qubit technology here, which is at the bottom, NISC approach, yeah, and say, okay, this may not, yeah, penetrate the logic that we need when we're defining the quantum circuit logic, yeah, the QC logic for any kind of field in any of those, you know, any of those domains. Yeah, so that's why these are still separate. You can have universities at country level, the companies, yeah, research centers, etc. But it should be international, an international collaboration. And I think HiPEAC is a very good example. Yeah. We do much more than quantum, let's say, in HiPEAC, right? Yeah, but we should maybe organize also a summer school for quantum computing students and researchers, yeah, in which we say, okay, let's look at the language, let's give some examples, the quantum gates, etc., and then you go away, and that is how we can create, let's say, this joint understanding or or consensus of the concept that we need, yeah. So that I think is important to show, yeah, such that at some point, and people asked me also, today I think, was an Indian PhD student studying in Spain, by the way, yeah, and he said, like, but how long do you think it's going to take before we will have, let's say, an operational quantum, yeah, he also used an accelerator on the market. I said, look, yeah, I think personally, and I'm honest, 10-15 years, and maybe it's closer to 15 years than to 10 years. Yeah, that is how much longer it will take before any of those qubit technologies stabilize in maturity, and that we can scale them up to larger numbers, that we can actually start using them on all kinds of applications. Yeah? So we need the quantum gates, we need the quantum circuits, but of course we need the quantum physics too. So we do need people working, let's say, in the gray box here. These are the quantum physics people. I was here for a long time, yeah, but we also can be here, because you see computer engineering is there, mathematics, yeah, we can look at the physics, but we can also look much more now at, let's say, the higher end applications. And this is when you go for a university or you go work for a company, you can bring that message, eh? You have that picture in the slides, yeah, so say, well, this is it, you know, yeah. You also have the NISC paper, yeah. I will say something at the end of today's lesson. Eh? I want you guys also to read that paper. Not for tomorrow, not for Thursday, but yeah, Friday, I want to have, let's say, an open discussion, maybe half an hour. Yeah, what do you get out of that? Yeah, whether it's complete bullshit, tell me. Yeah, we try to be very strict on what we write down. Yeah, and so far I get good comments, but maybe we're all wrong. Yeah, so if you think this is maybe, I kind of doubt that. Make sure that you bring that message to me, yeah, and then we want to update it, yeah, that we can. It's in the public domain. It's on archive, yeah. That's something I learned from the physicists. They write whatever their results they have. They put it on the public domain on archive, yeah. IEEE, for instance, starts accepting these things. Before it was completely refused. Now they know they cannot refuse it anymore, yeah. But the people. So this paper is on archive. Yeah, because I don't want 10 people to be reviewing it and then you're being killed for stupid reasons. And I said, okay, yeah, we just make sure it's very strict. It's very correct what we write down. Yeah, and we put it in the public domain. Yeah, and then we can, so if you Google, or Ecosia, that's another kind of Google search engine. Yeah, if you Google PISC and NISC, you will find the link to the paper, but it's already in the staple that you have there. Anyway, so these are important things, such that maybe in 10, 15 years, yeah, 20, 30x, yeah, we can start thinking, okay, maybe we integrate, maybe one of those technologies will be sufficiently mature, maybe 2 or 3 will survive. But never 6 or 7, because it's too expensive, too complicated. You can never have all of these technologies at an operationally qualitative level. Yeah? So that is, I think, very important to understand. And then we can really integrate again the quantum software that we already tested, that we know really works, to scale it up to larger number of qubits. That is the idea of this particular kind of graph. Yeah. So yeah. I just, and so this is at the end of the slide. Yeah, it isn't, literally, it is an open invitation. Not that I think everything else should be forgotten. This is not what I'm saying. Yeah, not what I'm saying. But if you think, okay, yeah, you want to really look at the future, computational future of this planet, not of your country or company, of this planet, we need to really collectively work together, yeah, on all of those aspects. And we can start really with the applications. If you have maybe a medical doctor somewhere, yeah, or a chemist, yeah, talk to that person, yeah, and then start looking together at maybe papers on quantum computational chemistry and all these kinds of things. You will discover maybe a lot of ways in which we can start collaborating, yeah. And so I will still start trying to get, let's say, at the European level, this collaboration with these let's say, these reverse triangles. Yeah, that is what I would like to have. Yeah, very difficult to get because it's about politics. And yeah, I'm a real scientist. I don't do politics, but yeah, okay, if you have to do it, you have to do it. Yeah, unless there's somebody brilliant in politics, say, yeah, Koen, I can help you with that. I'll be very happy to hear to get to know you, right? So that's also what I want to say. But again, it's your generation. Not old guys like me. I'm not that old, but still old enough. I cannot fulfill all of these things. We need a collective kind of thing, and it's the youth, you guys, who need to do that. And this is extremely important. If you look at our students that we have here, yeah, from electrical engineering, environmental, cybersecurity, and chemistry. Do I get computer engineers? No. There are enough computer engineers, by the way, here. That's very good, yeah. But you really need diversity of people and competences to start working together, and this is really the main message that I want to bring, yeah. Because, yeah, well, okay, I have to see. Why is that? Yeah, the multiple reasons, and of course the challenges, they still stay very big. They stay really very big, yeah. But if you look at quantum algorithms, and this is something I found on the internet, there are 2 references. Yeah, Wikipedia, I like all of these public domain kind of things, but also ACM has a similar kind of figure. Yeah, if you look at how many papers there are to which everybody in the world is referring to, 25. 25, you know, we produce many more papers individually here than those 25. Okay, they're very important, let's be very clear. It's not that we should neglect these things, no, very important. But we really have to step outside and start implementing or applying those kind of things, or inventing completely new kind of things, yeah, in other kinds of fields. And this is how we will massively contribute to, let's say, the quantum computing logic, that it really progresses, that we really can build systems that can reply and comply to what applications of this world need. Yeah, we all know global warming, all these kinds of things. Yeah, we cannot even model those kinds of things. It's impossible. Yeah? We don't have the compute power, not even the intellectual capacity to do these kind of things. So you need maybe a team of, let's say, the group here of people, have 40, 50 people, yeah, collectively start working on these things. You can have smaller teams. This is how you make progress. Yeah, that's what we at small scale we do in QBee too. Yeah, but this is extremely important. So for examples of topics. Yeah, and I got that actually from one of my students, this slide. Yeah, we need to really look at so many different fields, because if you only look at from your own little background, yeah, and then you turn this, there must be ways in which you can connect these kind of things. This simply shows machine learning, quantum mechanics simulation, optimizations, cryptography, finance, chemistry, other applications, space, yeah, that's what we're doing right now, yeah, and chemistry. These things are, so many things are interconnected. This is very challenging, yeah, and actually fascinating to see, yeah. So again, this shows what we're doing now inside QBee, yeah, and of course I try to connect to universities too. Yeah, but that is not so easy. Yeah, so we do this chemistry kind of thing. Yeah, the genome sequencing. Yeah, the pharma world is also looking at DNA to create new medication. Yeah, when you go to your medical doctor, he needs to look at your DNA profile. Yeah, we're not there yet. It takes about a day on very powerful machines to get your DNA out of a piece of hair or whatever it is. Yeah, your DNA profile. It should be, you go to your medical doctor, you put your finger in a device, up maybe 10 minutes later, let's say 1 hour or the day before, and then you get, for you personally, you get your DNA structure. Yeah, and then immediately there should be maybe some kind of medication coming out of your DNA profile based on your gene structure with this particular kind of symptoms that you get this particular medication. We need that for space too. Why do we need that for space? The question. We want to bring also ESA, European Space Agency, bring people to Mars. Definitely, yeah, we all know Elon Musk. Yeah, NASA also wants to do that. To deliver astronauts, yeah, or Marsionauts, whatever you want to call them, for the rest of their lives on the planet Mars. It takes 8 months by rocket to reach that planet. So you cannot say, oh, somebody had, let's say, a problem with the heart, and you send a message to planet Earth. That takes 20 minutes at the speed of light. Yeah, that's how long it takes, 20 minutes. And then people will look at it maybe, and they say, oh, okay, yeah, we have to look at it. Let's develop something, test it. Oh, okay, make a rocket, and then we put 8 months to go back to Mars. You see, this is not a feasible kind of way of sustaining these people going to that planet. Yeah, so they need daily maintenance, lifelong, on that particular planet for the analysis, but definitely also for the medication that you need to have. You see, these are all things that fit in our space program with Telespazio. Yeah, whether they want to go for that, yeah, we're still in the negotiation phase. But yeah, this is what I told them. This is what we need. Yeah, and let's say 2 weeks ago we were in Bruges, yeah, which is a city in Belgium. Yeah, still have, let's say, 7-8 minutes. Yeah, and then I will stop. Yeah, it was organized a 2-day workshop by ESA, European Space Agency. There were like 250 people present there. Yeah, a room bigger than what you have here was filled with people. Yeah, researchers, space researchers from all over Europe. Yeah, and so they really were brainstorming for 2 days on what are the scientific challenges that we need to work on for the next 2-3 years. 2-3 years, not 10-15 years. Yeah, quantum was mentioned only in the beginning because somebody from the German airspace organization, DLR, yeah, said something, why don't we talk about quantum computing and quantum logic? And then I said, okay, it's very good that he was there and he said that. So 2 minutes later I also said, yeah, I also want to say something. I'm very happy that somebody from DLR made that statement, because we have to start doing those things now. which they already do in Germany, by the way. Let's be very clear about that. Yeah, they start doing that at the European level too. That you really start saying we'll have calls for quantum in space, and whatever this quantum is very diverse, and that goes from humans, human health, yeah, to let's say the planet Mars, whatever is happening there, and all kinds of aspects. Yeah, so yes, you can do optimization and things like that, whatever the D-Wave is doing. Yeah, as I said, they're already moving into the quantum gates too. Yeah, and there's clearly also things. Okay, space. Yeah, I already made that link. Cryptography, yeah, or encryption, quantum encryption. That's a scientific community, a living one. Yeah, they already, and that's maybe 5-6 years ago, they already said we go into the post-quantum encryption. Post-quantum, because yeah, Shor's algorithm can crack any kind of RSA. How big your number is as a reference number, yeah, you can still crack it into the prime numbers that get that particular number. So you really need to go beyond the quantum logic kind of thing, what we're capable of doing. Yeah, so these are all aspects. That's also important for space, by the way. Yeah, if you have satellites communicating around the planet, there are 3,000-4,000 satellites continuously circling our planet. There's a garbage around the planet. Eh? Yeah, okay, very good operational things, but a lot is still flying around, and they should be removed. Okay, that's one of those challenges. We're not going to. QBee has no ambition in that. Eh? Yeah, but this is clearly a challenge we need to look at. Yeah, so. Very important for anybody who at some point wants to make the step to say quantum computing logic, whether it's at a university, a research center, or in a company, yeah, do not forget this particular statement. Every quantum algorithm, quantum circuit runs on a classical machine. Yeah, absolutely. We made our HiPEAC simulator, runs on this laptop, can go to, let's say, 25, 26 kind of qubits in superposition. If you have more memory, you can go to maybe 60, 70. But 70, you're already very close to the full saturation of memory on supercomputers. That is because you really use huge amounts of matrices, yeah, on which you apply all of these quantum gates. So you have to store that somewhere. Yeah. So there are still enough challenges. Yeah. So that is even for young people like you. You can have so many things you need to look at and try to solve. Yeah. One small side comment, and I was talking to the American lady who's also teaching on sustainable computing. Yeah, said, who on this planet is working on DNA storage? Yeah, I'm not talking about the genes and things like that, but DNA, the 4 amino acids. Yeah, storing that. You can make a DNA-based kind of storage device, yeah, not bigger than this, yeah, a couple of centimeters, which stores more than a supercomputer with all of these data centers that we're building, yeah, you know so but who is working on these things? What university is doing that? Some startups are doing that. So you do really need a lot of startups that do crazy things. Everybody says like loco. This is crazy in Spanish, right? Yeah, yeah. But yeah, that's what it is. People also said in the beginning, say like, computer engineer doing quantum, yeah, it's ridiculous, you know. Now they don't say that. Nobody says that anymore. Yeah, and I hope this week you will not say that to me anymore too. Yeah, that you say, holy damn, this is possible. Yes, this is possible. But if we don't collectively work on it, no, it will stay on paper, right? So this, I think, is extremely important to remember. This, yeah, 5 more minutes and I'm really done. I'm stopping. Yeah. Yeah, this is the blue thing here is the memory, the random access memory of supercomputers. So how many qubits can you put in superposition? 50, 60, maybe 70, depending on how big these machines are. China is very good in supercomputers, by the way. If you think the Chinese, it's only to eat Chinese food. The Chinese food in China is really good, much better than the Chinese food that we get in Europe. Yeah, that's my personal opinion, very subjective, I admit. Yeah, but this is, yeah. So this is, let's say, the limitation of how big our models can be using perfect qubits, yeah, and run it on a HiPEAC simulator on a classical machine. If you can go to 70 kind of qubits in superposition or full entangled, you already exhaust the memory of the supercomputer, because you have these huge matrices that you have to represent all of the data in, on which you apply all of these quantum gates. So the amplitudes are continuously changing. So this is one of the, so you follow maybe the MIPS course, very good. Because that's one way to make the move, let's say, to quantum computing logic too, right? So this is very good. And then, okay, you see here, this is what we should be having, and this is what we currently are capable of generating with classical hardware. But okay, so it says we can already do a lot of things. I will not go through this one anymore. So this is where we as a company, and with just one example, the highlighted things here, this is our, let's say, 7 to 8 year kind of a goal, but we're working on those aspects. And we have our own simulator. We use Qiskit, but we use also other kinds of platforms. Maybe I go back to the TU Delft platform, which grew out of my group, by the way, in Delft. So, but this is still not so certain. But this is what we do, and we need to have many more people, working on those aspects. Wait, okay. Express yourself in this microphone.
I'm really curious about auto QC and the program search and program optimization, what you're actually optimizing for there, and what's the state of compiler optimization in quantum programs and quantum compilers.
Very good question, and my answer is I don't know. It's Rui Maranhão and Shaukat Ali. Rui is from Portugal, and Shaukat Ali, Pakistan, but he's working in already his entire life, professional life, in Norway, and they collaborate on these things. So we still have to find out what that actually implies. So again, if I don't know the answer, I'm very open. I don't know. But I do know that they really said, no, keep us there. Because Shaukat Ali has now a couple of students who are doing his master, and they start a PhD in Oslo. And as soon as we have concrete results, we'll start integrating them again in some kind of Qiskit platform or our own platform, I don't know what, with the tools. But because they have to create, they have to get something from a quantum library or from a quantum application, and make changes here such that the open quantum that they let stream downwards towards the hardware is correct. But again, don't ask me the details. But Rui Maranhão and Shaukat Ali, these are the people that you can Google them. And you will for sure you will find papers that they're publishing. So okay, so this is clearly that we need to have, let's say, go to the physical qubits, but also to the perfect qubits, and then start integrating them at some point again. That is what we need to do. So now I'm gonna run blah blah blah. These are the PhD students, so the 4 guys that are sitting here, on that row indeed. So so you can talk, and I will not talk about these demos. I will talk about these things maybe later this week. This is also something, the routing and the mapping, because these qubits, they need to move around. You need to do a 2 or 3 qubit gate. They need to be close to each other. That depends again on what kind of qubit technology you're using, but they need to be close to each other to perform that particular kind of gate. This is just a simulation that we did. Voilà. We come to the conclusion, and then I'm only 1 or 2 minutes too late. So we need indeed, let's say, the PIS kind of approach. And these are all terms that I will maybe explain later this week. There's the NIS kind of approach, so purely looking at the physical simulations and the physical phenomena. So we get fault-tolerant quantum computing out of this thing, which I did for years in Delft. Surface code is like combining 49 physical qubits to make 1 logical qubit. So 1 out of 50. So that is the price that you have to pay, to have this instability in the qubits, to turn it into 1 stable kind of qubit, logical qubit. And then at some point we get, let's say, again, fault-tolerant quantum computing, if we can integrate all of these things again in an operational system, but that will take at least 10, 15 years. So I think that is basically the main conclusion that I want to have. And that we can again come to real operational quantum accelerators in the market that you can use for your post-PhD, your postdoc kind of work, or whatever work in industry that you will be doing. Thank you very much, and see you tomorrow.